All right, let's dive into one of the most fundamental forces in the entire universe, the electric force. We've all felt it, right? That little zap of static electricity. But what's really going on? Today, we're going to break down the exact rule that governs how every single electric charge pushes and pulls on every other. You'll see how one simple idea explains everything from why your hair stands on end to the forces holding atoms together. So, here's our game plan. First, we'll talk about that basic invisible push and pull. Then we'll get into a really clever trick physicists use called a point charge. From there, we'll decode the main event, Coulomb's law itself. After that, we'll put the theory to the test with some real-world problems. And finally, we'll make sure you're totally ready for any exam question that comes your way.
Okay, let's start with something we all pretty much know before we get into the heavy-duty math. We've all heard the saying, opposites attract, right? Well, in the world of physics, that isn't just a saying, it's a literal, fundamental rule.
But here's the real question. It's one thing to know that two positive charges push each other away. It's a whole other thing to ask, by how much? Is it a gentle little nudge or a really powerful shove? That's the exact question that a French physicist, Charles Coulomb, tackled back in the 18th century. And honestly, his answer changed everything.
So, it turns out this invisible force isn't random at all. It's perfectly predictable. Coulomb discovered that its strength all comes down to three things. First, the size of one charge. We'll call it Q1. Second, you guessed it, the size of the other charge, Q2. And third, this is the big one, the distance between them, which we call R. It's how these three things play together that gives us our answer.
Okay, so how do we build a universal law out of this? Well, physicists do something brilliant. To handle messy, complex problems, they simplify. They come up with a way to ignore all the complicated shapes and sizes of real things and just focus on the charge itself.
And that brilliant simplification is the point charge. Now, this is an idealized concept. It doesn't actually exist. You imagine taking all of an object's electric charge and squishing it down into a single mathematical point that has no size, no volume, nothing. It's a pure abstraction, but it's an incredibly powerful idea that lets us create a rule that works for everything.
Now, you're probably thinking, hold on, nothing in the real world is a point. And you are absolutely right. But this little approximation works beautifully as long as the charged objects are really far apart compared to their actual size. You know, think of two cars seen from an airplane. They just look like two little dots. It's the same idea whether you're talking about atoms or planets.
And this is a perfect illustration of that. If you take something like a uniformly charged metal sphere, it turns out that the electric force it creates acts exactly as if all of its charge was packed into a single point right at its center. This is amazing. It means we can use our simple point charge idea for real physical objects.
So now that we have our simplified point charge to work with, we can finally write down the actual rule. This is it. This is the moment we turn a simple observation into a precise, powerful law of physics.
Coulomb found two key relationships. First, the force is directly proportional to the charges multiplied together. So double a charge, you double the force. Easy. But the second part is what's really fascinating. The force is inversely proportional to the square of the distance. That means that as you pull charges apart, the force gets weaker really, really fast.
And when you put those two ideas together, you get this beautiful equation. This is the hero of our story, Coulomb's law. The force, F, equals the product of the charges, Q1 times Q2, divided by that R squared, and also by a constant term, 4 times pi times epsilon naught. It looks a little complex, but it's one of the true cornerstones of physics.
Now, for this equation to actually work, you've got to use the right units. Everything has its place. Force, F, is measured in newtons. The charges, Q, are in coulombs. The distance, R, absolutely must be in meters. And that other symbol, epsilon naught, that's just a special number called the permittivity of free space. Think of it as a conversion factor that makes the universe's math work.
Okay, theory is great, but a formula is only useful if you can actually use it. So let's roll up our sleeves and walk through a couple of examples to see this law in action. This is where the rubber meets the road.
Okay, check out this first problem. We have two identical point charges. But before you even think about the formula, you should spot two things. The charge is in microcoulombs, that's mu c, and the distance is in centimeters. We've got to convert those into coulombs and meters before we do anything else.
So, the solution is just a careful process. First, write down the law. Second, plug in your numbers, but make sure they're converted. 1.4 microcoulombs becomes 1.4 times 10 to the minus 6 coulombs, and 6 centimeters becomes 0.06 meters. You plug all that into a calculator, and out pops the answer, 4.9 newtons. And since both charges were positive, we know it's a repulsive force, pushing them apart.
All right, for our next trick, let's go from stuff you can see down to the atomic level. We've got an alpha particle, which is tiny and positive, near a big gold nucleus, which is also positive. The numbers are incredibly small, but the physics, it's exactly the same. And would you look at that? The scale is microscopic, but the method doesn't change one bit. We use the law, plug in the charges and distance, and do the math. The force is a teeny tiny 1.14 times 10 to the minus 10 newtons. That might sound like nothing, but at the atomic scale, a force like that is enormous. It's literally what holds our world together.
Okay, you've seen the theory, you've seen it in practice, you know it's coming next. It's time to put your own knowledge to the test with a couple of exam-style questions just to make sure everything has clicked into place. All right, have a look at this one. 2 point charges. But notice the key detail. One is positive and one is negative. So before you even pick up a calculator, what does that tell you about the force? It's got to be attractive, right? They're pulling towards each other?
So let's run through the process. We use our formula. To find the magnitude or the strength of the force, we just use the positive values of the charges. We convert the units, plug the numbers in, and we get 0.80 newtons. And since we already figured out they have opposite signs, we know for a fact this is an attractive force. Simple as that.
Now for a different style of question. No calculations needed for this one. This is purely conceptual. It's a classic for a reason. It tests whether you really understand the relationship at the very heart of Coulomb's law.
The magic phrase here is inverse square law. The force is proportional to 1 over r squared. So what does that mean? If you double the distance, you're not cutting the force in half. You're dividing it by 2 squared, which is 4. The force drops to just a quarter of what it was. Triple the distance, it drops to a ninth. The bottom line is, this force gets weaker, incredibly fast as you move things apart.
So if we boil everything down, what do you absolutely need to remember? Just these 3 things. 1. The force gets stronger if the charges get bigger. 2. The force gets much, much weaker as the distance increases, thanks to that inverse square law. And 3. The signs tell you if it's a push or a pull. Likes repel, unlikes attract. If you got those 3 points down, you've got this.
And that brings us to one last thought. Coulomb's law is perfect for 2 charges, but the real world is messy. It has trillions and trillions of charges all interacting at once. So what happens when you add a 3rd charge into the mix, or a 4th, or a billion? Well, that's when the fun really begins, and it all starts with mastering the simple, elegant law we just explored today.